Continuing with quantum theory and electronic structure of atom, we will go into electronic configuration, their rules, and some examples on how to fill up the electrons in various orbitals. So we learned about quantum numbers in the previous video. So here we'll just revise on it and learn how to use it to do the electronic configurations. You're familiar with, there are four quantum numbers: N, the principal quantum number; L, the angular quantum number; Ml, the magnetic quantum number; Ms, the spin quantum number. And you're also familiar with the values it can take. N can take values from 1 to 4, L can take all n minus 1 values, and Ml can take values from minus L to positive L, and Ms, the the spin quantum number, takes values from positive half to negative half. And I've also given the number of electrons which is possible in each level. Like n equals 1 can have 2 electrons, n equals 2 can have 8 electrons, n equals 3 can have 18 electrons, and n equals 4 can have 32 electrons. We have learnt in detail about all these things in the previous videos. If you have any doubt, please refer to that. And we also know that in the n equals 1 level, the 2 electrons, we refer it as 1 s2. S refers to the value of L equals 0. So if you represent each level by a number, the levels are 1s2, 2s2, 2p6, 3s2, 3p6. We will use this now and see how we can fill in the electrons in these levels. So let's learn about some of the rules that has to be followed in order to fill in the electrons. The first one is the Aufbau principle, and according to this, the lower energy orbitals are filled first. The figure on the right hand side tells us how the energies are arranged and the order in which it has to be filled in. So if you based on that, it's clear that we fill in the electrons in the order of 1s, 2s, 2p, 3s, 3p, and once you reach 3p, you realize that it is 4s which is lower energy than as compared to 3d. So 4s is filled first, and then comes 3d, 4p, 5s. Then if you follow the same thing, 4d, 5p, 6s, and so on. So it is good to write down the Aufbau principle. Aufbau is the picture to identify which is the lower level. So based on this, if I write the electronic configuration of sodium, it has 11 electrons. The electronic configuration will be 1s2, 2s2, 2p6. That makes 10 electrons, and 1 electron will be in 3s1. So the electronic configuration of chlorine will be 1s2, 2s2, 2p6, 3s2, and 3p5. And I've also given the electronic configuration of iron, and you notice that the 4s level is filled before 3d, because according to Aufbau principle, lower energy orbitals have to be filled in first. We have two more rules for filling in the electrons, and the second one is the Hund's rule. According to this, empty orbitals are filled first, pairing occurs later. For example, in case of oxygen, we have 1s2, 2s2, 3p4 as the electronic configuration. So in the 1s level, first the 2 electrons go in, and then in 2s, again we have 2 electrons with the opposite spin occupy the 2s level. There is no problem with this. Now let's go to the p orbitals or the p subshell, and there are 3 boxes in there. So what we do is we fill in only the empty orbitals first, and then the 4th electron pairs up only after we fill up the empty orbitals. So the next rule is Pauli's exclusion principle. According to this, no 2 electrons in a single atom can have the same 4 quantum numbers. Or in other words, we can have N, L, and Ml can be the same, but the spin quantum number has to be different, because we cannot have in one orbital 2 electrons with the same spin. So for the electrons in 1s2 of oxygen, the quantum numbers are the N, L, and Ml are all same, but the spin quantum number, one will be positive half, the other one will be negative half. Now let's use the rules and do the electronic configuration for some elements. For your reference, the Aufbau principle diagram is also given on the right hand side. The electronic configuration of phosphorus 15, it has 15 electrons. So use the energy level and then fill in the electronic configuration. So the same thing for cobalt also, and you notice that 4s gets filled in before 3d. Then I have done one for bromine also, and bromine has 35 electrons. The electronic configuration is longer and it ends at 4p5. Then the electronic configuration of cadmium, and we reach up to n equals 5 level and 5s2 4d10. Then one more element, barium, and you can see that it's pretty long to put in 56 electrons. So the element platinum, and when you fill in the electronic configuration, when you see the Aufbau principle, you see that it's becoming too big. Is there an easier method? Because if you use this way to fill in the electronic configuration, when you reach an element like uranium and all, it's going to be much larger, and you cannot be keep on writing these levels. So we have to find out, is there an easier method to do? Let's go ahead and find out. We can do the electronic configuration of elements using the periodic table. This is an easier method. A periodic table is given to you, and let's understand the periodic table first. The first two columns are the S block, and the columns on the 6 columns on the right hand side is the P block, and in the middle we have the D block and the F block at the bottom. And we will also number the periods as 1, 2, 3, 4, 5, 6, 7. I have just given the alternate numbers there to avoid congestion, so it will be more clear on which period is what. So once we have all these ideas, we will use this and do the electronic configuration of, say, sodium. So we know from previous experience, the electronic configuration of sodium is 1s2, 2s2, 2p6 and 3s1. So now look at the inert gas, which is just before sodium. That's neon. The electronic configuration of neon is 1s2, 2s2, 2p6. So if I compare the electronic configuration of sodium and neon, I can write that the electronic configuration of sodium as configuration of neon 3s1. So what do you understand by that is, if any electronic configuration of any element is given to you, just look at the inert gas before it. So for example, for phosphorus, the inert gas before phosphorus is neon, and therefore they just write down the electronic configuration of phosphorus as neon, and then come down, count. We'll come to the period number 3, and that's in the S block, and I can have 2 electrons in the S block, therefore it will be 3s2. Then go across, and you will see that I'll come to the P block, which is also 3p based on the period number, and count up to phosphorus 1, 2, 3. So it will be 3p3. You have 3 electrons in the P level. So I have done an electronic configuration of iodine 53. So the inert gas before iodine is krypton, and then I come down and I reach period number 5, and I have 2 electrons in the S column. Then I have 10 electrons in the D. So for D, what we do is we always take one number less than the period number. Since the period number is 5, it will be 4d, and I'll have full 10 electrons in the D level, therefore it will be 4d10. And then when I count up to iodine, you see that I can have 1, 2, 3, 4, 5 electrons in the P. Therefore the electronic configuration of iodine is krypton 5s2, 4d10, 5p5. Similarly, the electronic configuration of tellurium is also given. The inert gas before tellurium is xenon, and I come to period number 6. I have 2 electrons in 6s2, and in the middle I'll have the 4f level also, because the lanthanides and actinides gets included, and for an F group we decrease 2 from the period number. The period number was 6, therefore it will be 4f14, and then we have to cross through the D group, which has 10 electrons. Since the period number was 6, it will become 5d10, and then up to and it has only one electron in the p group. Therefore, along with the period number 6, it is 6p1. So this makes writing electronic configuration very easy. I have to just look at the inert gas before it and pass through the S, F, D and the P level in order to write down the electronic configuration. We will do more practice as we go ahead.